morning and welcome to Machine Learning in Plain English Part 2. As in my first session, Machine Learning in Plain English Part 1, this part also will not include any math or any programming. So let us look, before we get started, I would like to do a quick recap of what we did in the first session. So we looked at machine learning, regression, linear multivariate polynomial regression, bias, variance, underfit, overfit, training, validation and test sets, logistic regression, and what machine learning is not. So let us quickly go over here. So a machine learning, a program is set to learn from experience if it continuously improves on a task by measuring its performance on the task. So as long as the program is able to improve its performance on a task by measuring its performance P, then we can say the program has actually learned. And regression is just a method that allows us to estimate the relationship between two continuous variables, which is known as regression. Also we have logistic regression, which can also do classification, and very importantly the input variable or the input variables are also known as predictors, explanatory variables, independent variables or features, and the variable we are trying to predict is known as the response outcome or the target variable. So if we take a simple example, a regression, linear regression, we can draw different slopes and come up with this black line which we think is the best fit of this set of points, data points. Okay, so a quadratic equation will probably do a better fit, and a polynomial will be kind of give you a wavy fit. And there are two important measures, bias and variance. Bias is when the model does not take into account the variation in the data, that is, it has a fixed sort of inclination towards the data, so it is not it is biased. So variance is when the model takes into account all the different variations of the data and is kind of squiggly or wavy. So we can see this particular slide where you see in this first chart there is an underfit or has high bias because the line does not take into account the variation in the data, whereas in this second thing it has a good fit. So because it does slope towards in the way the data changes, and in the last it has a high variance because it is very quickly, it takes into account all the variations in the data, so it has a high variance and it's called an overfit, whereas the first one is called an underfit and the center plot is called a good fit. And what exactly are we doing when we do a good fit? What we are doing is we are trying to minimize the distance between the data point and the estimated line. That is what we are trying to essentially do. And how do we do this mathematically? We can do this by minimizing the distance between the data point and the estimated line. And minimization, if you know, if you are aware of a little bit of calculus, you know that minimization can be done. Minimum of functions when you take the derivative and its slope is equal to 0. And the way minimization is done in machine learning is a technique called gradient descent, where we choose an arbitrary point on a surface and then check the slope at that particular point and move away from the direction of the slope towards the minimum of the surface or the curve. So this movement, we gradually move along this direction towards this minimum. However, gradient descent can also take you into a local minimum which may not be a global minimum. So this particular point where we have the minimum will give you the value of the weights or coefficients of the features, that is how much you should weight the different features to give you your corresponding output or response variable. Okay, there is a measure called R squared which will help you to determine, mathematical measure, how well your model is fitting to the data. And then we have something called multivariate regression, that is, in the previous case we just saw a single input variable and single output variable, whereas if you have many features. So for example, you have many features in a house, the number of bedrooms, the number of rooms, the square feet of the house, the location of the house, whether the house is close to a particular school, hospital or airport. All these factors or features actually influence the cost of the house. So when we are doing a regression, we have to take into account all these particular features or factors. And gradient descent is also used in this kind of regression, and this is known as multivariate regression. Okay, and when we do this multivariate regression, we can also compute something known as the p-value. A p-value less than 0.05 means that the variable actually influences the target and it is very significant, whereas if the p-value is greater than 0.05, then it is statistically insignificant. And the way we do this, we do training is we take a data set and we split the data set into a training and test set. This test set is also known as holdout set. The training set is about 70% of the data. We train different models and tune it till we get the best R squared and best performance and the lowest mean square error. And then when we are sure that our model is performing well, we test it on the test set. Another alternative approach is when we split into training, validation, test set, so that we can try out different models, test it on the validation set, and then finally we test it on the test set which is not yet been seen and ensure that it performs well. Okay, this so far we've seen regression of a continuous variable. We can also do regression of a variable where the data response is one of two classes, binary classification, or one of many classes. And when you have binary classification, we use something known as logistic regression, and we use a function called sigmoid, a mathematical function which takes one of two values, and a value which is greater than 0.5 is considered as 1 and a value less than 0.5 is considered as 0. So this function is used when we are trying to compute a response of a variable which falls into one of two classes. As you can see, this function takes one of two values. And then we saw these different classification measures. Now machine learning is not curve fitting, so we are not trying to fit the best curve that touches all the points, nor are we trying to only minimize the mean square error or the what we are trying to do, machine learning model needs to do is to generalize well. It needs to provide the best fit while also doing well, performing well on unseen data. So that is very key, and that is what the whole challenge of machine learning is about. So now, having seen what we did in the first session, let us quickly go to our second session. So I have left out a particularly important method of regression classification, which is known as KNN or K-nearest neighbors. The way K-nearest neighbors works is we specify the number of neighbors for the regression to consider, and the regression algorithm will consider the average distance of these neighbors and compute the point. So for example, in this particular old example of age and salary, let us say we choose a nearest neighbor number of 3, then what it will do is it will take the average distance between these 3 neighbors and come up with a predicted point here. Okay, then it will take the next 3 neighbors and it will come up with the next predicted point, next 3 neighbors, next predicted point, so on and so forth. So it can just see how the performance of the neighbors are, and it will assume that another point will lie close to that particular point. So that is what K-nearest neighbors regression does. Similarly, we can also use K-nearest neighbors. Okay, and one thing is, if we choose this value of K can be either 1 or it can be any other integer, 10, 15, 20, 25. When we choose a small value of K, since you're only looking at one neighbor, it will try to mimic very closely to the actual data point. So in other words, it will tend to overfit. Okay, but if you take a very large value, if you take like 25, 30 or something, a K of 30, then since it's averaging out over a larger set of points, it is going to underfit. Okay, so it will have less variance. So typically the values that are chosen are between 5 and 10 to give you a very optimal performance. So once you choose these different values, you can use some measure like R squared to determine how well the fit is. We can also use KNN for classification. So for example, if we have a toy example where we have age of people who have taken loans, and then we have the status, whether they paid the loan or they defaulted on the loan. The stars are the defaulters, and the blue triangles are those who paid the loan. Okay, so what happens is, again we choose k nearest neighbors of 3, and it look at the closest neighbors, and since all the and it'll take a majority vote. Since all the 3 neighbors are have paid, it'll take a majority vote, and it'll decide that it's going to be this particular person. Let us say you wanted somebody with age 33, it'll say is going to pay it. Then it'll take the next 3 neighbors, and again it'll take the majority vote. Since you have 2 paid and one defaulter, the majority is paid, so it again choose it as paid. Then it'll take these 3, since all the 3 have defaulted and the majority is defaulted, so it will make it as default, so and so on and so forth. So k can be any value, and you can choose a value between 5 and 10 for optimal performance. Now we saw in an earlier session that the way you build a model is you have a 70% training set and a 30% test set, or a 60 plus 20 plus 20. But these methods typically have certain problems. One is this holdout method can tend to overfit the data, and it may not perform very well on another sample taken from the same data set. If we randomly choose a new data set, it may not perform too well. Okay, so the other issue is that in the holdout, sometimes we may not have as much data as we want to have the 70% 30% partitioning ability. So there are 2 techniques which will help us when we have slightly insufficient data, and also to give us a much better estimate of how much error this your model will give. And there are 2 methods. One is known as leave out 1 cross validation and k-fold cross validation. Leave out 1 cross validation, what it does is it will use n-1 data points as your training, and it will test that trained model on your nth data point. So it will do this for all different n combinations of n-1 data points and testing on the n data points, and for each of these models it will test and compute the error, and finally it will average out the error. And this error that we compute over by averaging out over all n different models will give you a much realistic estimate of how well your model will perform on new data. Okay, so here this is shown diagrammatically. So here you have n data points. You use n-1 data point as your training and the nth as your test. That's the first model. You compute the error, which will be the mean square error. Then you choose another data point. You just move it 1 point left. Make this n-1 as your test set, and the remaining n-1 as your training. You build a model and test it on this data point, and you keep doing this n times. So the blue is your training data, and the single brown data point is your test. So you do this n-1 n times, compute the mean square error for each of these models, and then average them out. And this average will give you the most reliable estimate of how well your model will perform on new data. The other method which is equally well used is this k-fold cross validation. So instead of partitioning as n-1 and 1, you partition your data set into k folds. K can be maybe 5, 7, 9 or 10, whichever you want it to be, and you train the model on k-1 partitions and test it on the kth partition. And for each of these models, you will compute the test error or the cross validation error, which is really the mean square error, and you will average out this mean square error for all the k combinations, and that will give you a realistic estimate of the performance of the machine learning model. So here I've taken a 5-fold cross validation. So here I have 5 partitions. 4 of the partitions are training data and the 5th is the test. So I will test a model, I'll create a model here, test it out here, test out the error, compute the error, then I'll train another model here. Again, this will be the test, compute the error here. So I do this 5 times for all these different combinations and compute the error in each case and average out the error. So this will give you a very realistic and reliable estimate of how well your data, your model will perform on new data. Okay. Now let us look at some other advanced regression techniques. The name multivariate regression has the following problems. One is when you just have a 70% and a 30% and you just use all the features and you build a model, it'll tend to overfit. It'll follow the thing too closely and may not perform very well on a new data set. Okay. Secondly, the other issue is that some problems will have just 5, maybe 10 input features or 20 input features or 30, but there are situations where you will have maybe thousands of input features or maybe even 10,000 input features or predictors, and you may need to predict an output or response variable. It becomes very, not all of these features in these 10,000 features are going to be relevant, and then they're not probably going to affect your response variable, and in fact it may help to actually remove some of them to get a much better performance. But how do we select which of these features to remove? One approach obviously is to use the p-value, and a p-value which is much greater than 0.05, we can say it is not going to influence and it is statistically insignificant. There are other methods, and the main methods are best fit, forward fit, backward fit, L2 regularization, and which is known as rigid regression, and L1 regression, which is also known as lasso regression. Okay, so for doing this comparison of models, there are certain statistical measures. For example, BIC, AIC, CP, and adjusted R-square. BIC is patient information criterion, AKK information criterion, Mallow, CP, and adjusted R-square. These are measures, statistical measures, which you can use to compare different models and pick the one which is the best. So for example, high adjusted R-squares means the model is very good. So, or a low CP, low AIC, or low BIC is good model. Okay, so if you have many features, so for example, if you have data where you have x1, x2 up to xn features and a target variable y, and you would like to estimate a function, how do we go about it? So let's look at the best fit approach. So you have n features and you're trying to estimate a function, and pick just those features which you think are going to give us the best model. The way best fit approach works is it does an exhaustive search. It tries to look at all possible combinations of features. So it'll first create separate models with single features, compute the statistical measures. That is, whenever I say statistical measures, I mean the adjusted R-square, BIC, CP, or AIC, and then it'll take a combination of 2 features, again compute the statistical measures, combination of three features, again compute all the statistical features, and it'll do that for all the n features. And finally it'll have a big table of the different models and the corresponding statistical measures, as adjusted R-square, BIC, AIC, or CP, and then finally it'll pick that model which has the best statistical measure, that is the highest adjusted R-squares or the lowest CP, BIC, or AIC. But best fit approach is very performance intensive, since it has to do an exhaustive search, so of every possible combination of features. So you could easily run into a combinatorial explosion of features. So I've seen that even with 13 features, exhaustive search has to go through almost greater than 8,000 possible models to pick out the best model, and it is very performance and generally probably not used as much. There are 2 other approaches, the forward fit and backward fit, which are actually a class of greedy algorithms. That is, they will pick what they think is the best at the particular point in time. So the way the forward fetch approach works is, first it will take we will start with the null model, and then we will create separate models with single features, and then select that model which has the best performance as far as the statistical measures are considered. Then with that selected model and with that selected feature, we will add another feature from the remaining n-1 features. Now for this 2-feature model, we'll again compute the best statistical we will pick the best statistical model based on the statistical measure exam, namely adjusted R-square, CP, BIC and AIC. And similarly, once we have the best 2-feature model, we will add one more feature from the remaining n-2 features, and so on. We'll keep continuing it till we get the best model with respect to the statistical measures. The reverse approach is the backward fit approach, where we start with all the features and then we drop one feature from this model. Every one we drop we create n-1 different model by dropping one of the features, and then pick the one which had the worst performance and drop that. Then we will again take we'll drop one more from this remaining n-1 features and pick the best model n-2 model with the best statistical measure, and similarly we'll keep dropping till we get the best overall model. Now forward fit, best fit and backward fit are a way of actually going through multiple methods of iterations to pick out the best model, and we use these statistical measures. However, there are two other techniques which are very commonly used, which are known as regularization, which will do this process of selecting features automatically. The first is known as ridge regression, also known as L2 regularization, and the second is L1 regression or lasso regression. What ridge regression does is it penalizes the weights or the coefficients such that those features that do not have influence on the target or response variable are reduced almost to zero, and even other weights are actually moderated. So basically the regulation tends to moderate the weight so that the model does not overfit. So that is the key. So in this particular chart here, you can see if we start from the right hand side, these are all the weight coefficients for the different features. As you change this value of alpha, the weights start dropping, and for example a value of, let us say this may be about 40 or 50, many of the coefficients are actually going close to zero. So all these coefficients are going close to zero, and some of them are actually have some value. Okay, so that is what regression does. The other thing, the lasso regression, what it does is it again penalizes the coefficients, but in a slightly different way. But the advantage of lasso is, instead of actually making the coefficients close to zero, it will actually make them zero. So again, you can see these coefficients have these values here, and as you move towards the left, these coefficients start dropping. And for example, if I take a point here 0.6 or 0.7, many of the coefficients have actually reached zero, while some are still there. So this lasso automatically removes features which do not have influence. Though it is true that lasso does remove certain features, what I have read is that the ridge regression is more commonly used than the lasso. Incidentally, all the things that I've discussed in my previous session and in this session have been implemented as R and Python algorithms with all the corresponding measures and charts. So feel free to take a look, and it's actually available on Amazon both as a Kindle and paperback. So check it out if you're interested. So before I close, I would like to quickly go through, recap what I had discussed in this. Initially, we started with KNearest Neighbors regression and classification. KNN regression basically takes the average of the distance of the neighbors and plots and computes the new point, estimates the new point. Whereas KNN classification, depending upon the number of neighbors, it will actually take a majority vote and classify it according to the majority vote of that class. Okay, and then we saw cross-validation techniques, which is typically used when there is not sufficient data and we can't do the hold-out approach of 70-30. So there are two methods: leave-out one cross-validation, where we train on n-1 data points and test on the nth data point. We do this n-1 times, and each time we compute the error and average out the error to get a more realistic estimate of the error. The other option is to use the k-fold cross-validation, where you divide the data into k-folds or partitions, and you train on k-1 folds and test on the kth fold. You do this k times, and you average out the error. Other techniques are best fit, forward fit, and backward fit. Best fit actually does an exhaustive search of all possible combination of features, and you can run into a combinatorial explosion, but you'll get the best and perfect model. Forward fit, it keeps adding one feature at every step and picking out that feature, that model which has the best statistical measure. Backward fit starts with all the n features and keeps dropping one feature which has the best performance, keeps dropping them one at a time at each step till it comes to the best model. Then finally we have regularization, which can help in preventing overfitting and also in feature selection. So we have ridge regression and lasso regression. Ridge regression actually makes the coefficients close to 0 but not 0, whereas lasso actually makes the coefficients 0. So, and automatically does the feature selection for us. Okay, so that's all I had in the second session. Thanks for listening.